All right, well, I guess I spoke too soon yesterday about not closing the door at 7:30. Yeah. Later. All right. So, yesterday we left off with the primary circuit, but talking with Kelly, I got to back up a little bit because she told me that everybody who did an oral today is terrified of being shocked by the magnet.
Only I learned now.
And I talked about this yesterday. Did that hurt? Did I shock you? Why not?
Because there's no current. There's no voltage in there with magnets.
It's not a wire.
Is there any electricity in this?
No.
Let's hear everybody. Is there anybody who thinks there might be electricity in this?
No.
Not anymore.
Okay.
Not anymore.
In the manual, it talks about something about how the secondary circuit grounds to the iron core.
Okay.
No issue. No electricity on.
Maybe Kelly misunderstood and they were afraid it was going to...
No, I kind of heard. All right, the next person who thinks that a magnet is going to shock them, I'm going to shock you with it.
Shock you with it.
Shock you with it.
Shock you with a concussion.
Now, the rest of you aren't scared because you know I can't, but some of you might be. All right, so here I have a magneto. Just happen to have one sitting here. And inside of it, it has a rotating magnet and pole shoes.
And extensions.
An extension. I'm going to put my fingers in there. I'm going to turn it. Ah! No. Am I going to get shocked?
No.
Okay. So everybody's going to stop it with this business about electricity is flowing through the magnetic circuit. Is there electricity flowing through the magnetic circuit?
Absolutely not.
Okay, so here I have in black the magnetic circuit. I have a rotating magnet. I have and a core. And as this magnet rotates around and round, what goes through the pole shoes, the coil core, and back around? Magnetic flux. How many amps are going through that?
0.
Are you positive about this?
Yeah.
How many volts are going through it?
0.
Okay, we have no amps, no volts. How much power?
0.
0. What goes through it? Magnetic flux. Is everybody on the same page with this? Now we're going to move forward a little bit. Or should I just end it right there? Spend the rest of the day right there. Okay, so no voltage is going through there. So I have this blue line right here. What does the blue line represent? What was I drawing there? The rotor magnet. And what did I call that? The static flux curve. And so that's what's going to happen without the green. What does the green here represent? Primary. So without the primary, I'm going to have a static flux curve. But then I add the primary, and what goes through the core right here?
Magnets.
Just magnets. And so the magnetic flux is going through the core of the coil. The core is made out of soft iron. Laminated soft iron. And how much electricity is flowing through said?
0.
0. Okay.
Only magnets.
Only magnets. So we have this magnetic flux going through the core. And what does that flux do? It expands out and it cuts. Okay, for those of you who are keyword people, if you can't, if you're doing the orals, they got the magnet and the thing and with the flux and the cuts across. Throw that one in there somewhere. I kind of feel like you should write all your notes on cards and just go like that. Just go, there you go. There's my oral. Make it rain, man. I gave him all the words. So we've got magnetic flux is expanding out from the coil core, which is metal, which has no voltage in it. It expands across there and it cuts across the primary coil,
Yes.
which is the smaller of the two coils. talking about 100 or so windings in there. Cuts across that, and what does that do?
Creates current
It
and
creates a
voltage.
current and a magnetic field in the primary.
Well, you're just going too fast because that's what's happened to oil. And it creates it jumps across and it goes, and power.
That's spark plug.
Yeah.
And spark. Yep.
Reminds me when I was a kid, I loved Andy Griffith Show, and they had Floyd the Barber, and it kind of talked like that, you know. So anyway, you have to watch it. But okay, so the magnetic lines of flux expand out. They keyword cut across the primary coil, which
Creates
induces current in the primary. So now I got current in the primary. Okay. What does Lenz's law say about all this? It's gonna, I heard it over here. It's going to counter. It's going to counter whatever causes it. Whatever causes it makes it want to not do that. So I'm going to add something else to this. I have the static flux curve, but I've just created a magnet in the primary. So what is that going to do to the, I'm going to regret this one. What is it going to do to the magnetic lines of flux that are running around through that magnetic circuit? It's going to not like that. And so it's going to tell it to not do that. So we have the static flux curve, but that is going to kind of get distorted out. Maybe I should make it like dotted. And that's when the static flux curve tends to look a little different, what it's doing. Not that that's a big deal, but it does change what it looks like. And so we have the static flux curve. So it modifies it only because there is voltage and amperage flowing in the green part here, which is the...
coil.
No, it is not! It's the what?
Primary circuit.
All right. The primary. So we have voltage flowing in the primary, which creates a... Everybody's afraid now. I'm not saying anything. I can't get yelled at me. Magnetic field is correct. Where did the magnetic field come from?
Magnets. Magnet cutting.
Okay, so magnet 1 is the we have magnet 1, magnet 2, and magnet 3. There's 3 magnets going on here, right? So far I only have 2. So magnet 1 is a pure magnet. It is the magnetic circuit which cut across the primary, which induced a current which caused a magnetic field in the primary. So I have 2 magnetic fields so far, and the magnetic field in the primary screws with the magnetic field coming off of the magnetic circuit, so we get from a static flux curve to resultant flux curve. All right, then, now that we have this current flowing in the primary because the lines of flux in the magnetic side expanded out, cut across the primary, cuts across the primary, induced a voltage at the primary. I now have voltage flowing through the primary. All right, so yes, I do. There's voltage and amperage and power going through this green part, the primary. See this little ground symbol? Okay, that is just...
connection.
You know, I could have just done it like this. Right there. And attach that back to that. Yes?
Yeah.
So that's the same thing. It's what it does. So when your book says that it grounds it back to the pole shoes, it just connects it there. So what is the power doing? Well, it's going to start in the coil, and it will go through here, not capacitor, through the closed points, back around, touches the metal frame, flows around the metal frame, comes back this way, and have a complete path going all the way around. But it just doesn't look nice to do it that way, so they draw it differently. And yes, it is grounded to the frame to make a complete circuit. Because you have to have a complete circuit. Otherwise, you don't have current flow. I should have started there. There should have been something I should have said on week 2. I'm sorry. So we have a current flow now through the primary. Yes?
Yeah.
Okay, current's flowing through the primary. So because I have current flowing through this here winding, and I have this expanding, it's hard to draw, expanding flux. What color should we use? Red?
Blue is flux.
Purple.
That's what I said, red. I don't have purple. I have pinkish. I guess I could make it kind of purple. There, like that color? Okay. So now, over all of this, I have a whole bunch. Can I do it that way without screwing up? I have thousands of I shouldn't have made them fatter. Should have made them skinnier. That was a mistake. Because the green ones are fat, technically, and these ones are really skinny. Because there's so many of them.
Is it 100 times the primary
Like
one?
1,000 times. Something like that. It's a big step up. So I've got my, right, so all the secondaries in there, right? So the secondary, well, the secondary also has to be grounded, right? So we'll ground that out. And the secondary is going to come up. And it's going to go out where I have room to draw. Schematically, it looks like this. Physically, it does not. So that's going to go to a distributor finger. So I'll represent like that with learning my lesson. Just make it a 4-cylinder. Save time, see world. All right. So that is going to go to spark plug. This is my schematic for spark plug. And to ground. Now, what does that look like really? You have a wire that is going to come out of the distributor, goes to a spark plug. The spark plug is screwed into the cylinder, and because this is metal and the cylinder is metal and the cylinder is grounded, that's its path, right through the cylinder, through the case of the engine back around. Now, so we got that going. We built it, but what's really happening? I already told you. So we have that flux is built up in the primary. So a little bit of magnet in the magnetic circuit causes a bigger buildup in the electromagnet, which is the primary, which expands even greater, because otherwise we could just do this in one step. Just wrap 1,000 windings around the core and just go magnet secondary, right? We can't. It's just you can't go up that high. You got to do interval. So got the magnetic primary builds up, and it builds up. I got my green over here. And so what's happening is that kind of wants to follow all of this. In my mind, it tends to follow like this. It's working with the resultant flux. But right about here, 10 degrees past neutral, what happens? That's my E gap. Points open. Points open. And when the points open, this whole thing just drops to nothing. Right? More vertical, more vertical. There you go, more vertical. And it's going to then follow and start to pick up. And then it does the whole thing. And then over here, points open again. Here's neutral. So points open here. E gap, points open there. Does the same thing. And every time it does that, it is this massive, rapid collapse of the which circuit? Primary, because the point's open. And so, bang, collapses. We have 100 windings over 1,000 windings. Huge step up transformer. So we go to 20, 30,000 volts into the pink, and the distributor finger will line up to the correct one. And because it is an AC system, one time the spark is actually going to jump that way, and the next time the spark is going to jump that way. So if I look at just by the way, there we go. So there we go. These are spark plugs right here. This is a massive spark plug. This is the fine wire. So same thing, fine wire, massive right here. So one time, this is going to be the positive, and this is going to be the negative. And the next time it goes, this will be the negative, and that'll be the positive. So one spark plug is going to live its life as the middle positive, and the next one, its buddy, is going to have its life as the negative. So if I go back to discard this, I would say, like, this would be positive, this would be negative, this would be positive, this would be negative, then positive, negative, it's just going to keep doing that. So one spark plug's always going to be negative, and the other one, his buddy's going to be always, next one in line will be positive, which is kind of a weird thing. So while I'm on that subject, I could just say they tell you to rotate them. And some people say, well, you rotate your spark plugs because this is positive and this is negative, and since current goes from negative to positive, what happens is every time it sparks from the outer electrode to the inner, it takes a little microscopic piece of metal and shoots it across, and it kind of welds itself to the center electrode. Now, if that were the case, then the center electrode, in my mind, would get bigger and bigger and bigger, and this outer one gets smaller and smaller. And I say, well, then swap it. Never have I, in all of my years working on an airplane, pulled out a spark plug and go, wow, look at the size of that center electrode. Boy, that thing's really going negative to positive. They just wear. I don't know. People come up with craziness. So why do you rotate spark plugs? Well, yeah, they say it has to do with that. But you always go tops to bottoms because it allows these junk to get out of them. But we'll get into that later.
Take a little piece of metal off one way, wouldn't it take a little bit back the other way?
Well, that's the theory. So, well, no, because this spark plug doesn't go back and forth. It's always from the outer to the inner. And the one next to it is always from the inner to the outer. Yeah. Anyway, don't worry about that part. So, okay. Just thought I would. Nope. Not if I haven't written it yet. Okay. So we're still back on the primary, but I've kind of explained the whole thing. So hopefully that helps you with your oral. So those are, what we're looking for when we're asking you these questions. How is the electricity produced? How does this work? Should we do it again? I don't mind. So, all right. So you have the primary magnetic circuit, which consists of rotating magnet, pole shoe extensions, and the coil core. What is flowing through that? Magnetic flux. Where's my rotor? He's gonna get it while he had his eyes closed too. I couldn't even imagine.
Eric almost got shocked by a rotor.
I know. I'd take it over there and just spin it next to you. I'm gonna bring a drill in here and put on the end, and I'll really fix you. All right, and so we have the magnetic lines of flux are expanding out from the coil core, cutting across the primary, which causes in the primary circuit current and voltage, which causes an electromagnetic in the primary, which causes the magnetic lines of flux in the primary to expand and cut across the secondary, which
Sparks and spark plugs.
well, it kind of grows at a rate that really doesn't do anything. So now it cuts across and it's just sitting there across the secondary, waiting to happen.
Breaker points open.
Then the breaker point's open. Then that field, wham! And then we have 20,000 volts.
And sparks.
Now, the voltage that is produced depends upon the gap. If you have a big gap, voltage builds up until it can jump across. Or if it's too big of a gap, it just builds up until it can break something inside the magneto, find an alternate path, do something. But if it's, teeny, tiny, it's not so much because it jumps it real quick, and that was the current flow. You get current flow and then it dissipates and it's done. So a lot of the voltage is dependent upon how big the gap is. When you test a magneto on the test stand, the manufacturer tells you how big those gaps should be. And you'll see it when you do it. They're not random. They're exact points at a certain, I want to say, some are 5 and some are, say millimeter, that's not right. I use drill bits, but it says right in the manual which ones you're supposed to use, so I just set them with drill bits. But they're an exact gap. And I will tell you something else. There's a thing called the coming in speed of a magneto. What does that mean?
The minimum rate that it can spin and still produce a hot enough spark.
The minimum rate it can spin?
It will spin.
Not spin any speed I want to.
It's the minimum speed that it will spin and fire all the points on
Okay, it's the minimum speed that you must. The coming in speed is the speed that you turn it in which all gaps fire consistently. So you turn on your magneto on the test bench and you turn it up slowly until you get tick, 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 and it goes consistently. As soon as it goes consistently, and by the way, there's a way to cheat just a little bit. When you do a magneto and you freshly overhaul it, spin it up fast. Go to 200, 300, 400, 500 RPM. Let it run for a second, right? It burns off some of the dirt and stuff. Then bring it all the way down. Then bring it up a little bit until you get consistent tick and let it run. See if you can take it down a little bit, see how good it can be. But it must consistently, if it's a Bendix, must consistently fire all gaps, all sparks at no more than 150 miles an hour. Yeah. 150 RPM. Well, wait a minute. It's got an impulse coupling on it.
Yes.
If it's got an impulse coupling on it, how many RPMs would I need to do to consistently fire?
A rotation.
Yes.
The speed at which I would have to rotate this to get this to consistently fire all four of those is
Double engine speed.
1 revolution per billion years.
Yeah.
Because eventually it will tick it and it will go. So there is no coming in speed with an impulse coupling. You can't check coming in speed with an impulse coupling. It would fire consistently at 1 RPM, right? 1 revolution per minute.
Because the spring's gonna throw the.
Because the spring's going to wind it up and make it go. That's the whole point of this thing. Because when the engine is turning over slow, and I didn't have an impulse coupling, would it fire? Yeah, so if my engine's turning over and I'm rotating this at 50 RPM, am I going to get any spark?
Nope.
Fat chance. If I turn this over at 1 RPM, am I going to get consistent spark?
Yeah.
Yeah, okay, so that's what this is about. So you can't test your coming in speed with an impulse on. You got to take it off. And that's how you test them. So now the impulse, if you read the manual, it'll tell you it should disengage at a certain RPM about. And so you check that. You can see, well, does it disengage? But that's a whole different thing. So the coming in speed of the magneto is a test to see how good it is. So let's just say you built your magneto and you put it together and you put it on the bench and it kind of, you run it at 150 and it's tick, 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 tick. Is it good?
Nope.
No. So you spin a little bit faster, get it up to 200. Now it's firing all of them. Is that good? No. Why not? Kind of what it's telling you is it's got to spin faster to make it work, which is what, if you look at the drawing, think about what's happening. You are taking this blue curve and you're shortening it, you're increasing the frequency, and so it's making things happen faster. So you're cutting across those lines of flux faster, which is creating more electricity in the primary, which is then creating more in the secondary. So it's just that collapsing happens faster, which is more voltage. So the faster you spin the magneto, the hotter it's going to get. Bring it all the way back. At 150 RPM, you're not spinning it very fast, so it's really got to work well to make this happen. So if it's not, then you didn't build it correctly. You got something on the finger that's blocking it, maybe one of the towers. Now, if it's consistently going 1, 3, 4, 1, 3, 4, 1, 3, 4, and you got a problem with 2, well, then you can isolate it down to what's different about number 2. It's the finger, it's the distributor, it's the wire coming out of it. So think about that. All right. Did you learn something?
Yes.
Learn I get real excited about some things, didn't you? You learned that I was bluffing about throwing things at you. Did I tell you? I think I told you when I was a adjunct. I mean, this is a long time ago, back when we were still on main campus. I was doing something, and I was like, I think I was like the lab assistant or something, because I think Kit was there. And then, whoosh, bang! Some kid threw a magneto at another student. I just had enough of that student. He just picked it up and threw that magneto across the room and missed the guy, but it hit the wall. Like, I'm out of here.
That kid's got anger issues.
Yeah. Like that meme where Homer backs up into the veg.
Yeah.
That was me. Breaker points. All right, we're going way back now. Breaker points, also called.
Contact assembly.
No.
Right?
I mean, yes. Also called contact assembly. Contact assembly or contact points. Or points. I'll put points. 2. Points are open and closed by the rotating cam. Closed by the rotating cam. Three. Well, it's singular, so its job is to open and close the primary circuit. For the P lead, what is the P lead? It is the ground that goes where? To the ignition switch. I do not have it schematically drawn in here, but if I did, I would put it right here. There, I put it right there. So that when the switch is open, the mag is, and when it's closed, it's, wait a minute. Listen to you guys. So it's backwards. I shouldn't have put it there.
So when you turn the key, it opens it?
It's, no, it's not really there. Hang on, let me put it in.
Between the contact points?
Yeah. All right. It really goes on this side over here. And it runs parallel off this side. And so what it does is it prevents your contact points from having any effect. So I think schematically I could put it like in parallel with all of this. So, but physically, it's really attached to this point right here. So that would be in the on position. Okay. And then if I close it, what happens is that when the breaker point's open, who cares? It's already grounded out right here. So you don't get the rapid collapse of the primary circuit. It never collapses. It just follows the resultant flux curve around and around. And it's just not enough to create a spark. So that's our P lead right there. And it literally attaches on the Bendix magnetos right here to these places right here. Or this one.
I finally understand. why
Right there,
P
that
leads
screw
so
right on top.
dangerous.
What's that?
I finally understand why it's so dangerous with not wired.
Yeah. Slicks are a little better. They have it right out here on a screw. It's on the end of the capacitor. So,
Actually say P lead right there on
Mm-hmm.
it does, and it has the torque too on it. Bendix, you have to have the cover, which you guys don't have, and it slides down in the cover.
Who thought of the name PD? Why not ground wire or something?
Primary lead.
Oh, makes sense.
Rare.
I was hoping I had a picture of it. I do not. I'm prepared. No, just thought of something new. Okay, P lead is connected to points. P lead is connected to points. Oops. Well, it's really more of a Bendix. They're connected to the points, but electrically, yes. Two points. Let me see. What do I got here? We'll do this. Points consist of, because I got a bunch of stuff here, we have a cam follower. Cam follower. There's some points. This is a little plastic thingy on there. These are slick points. Here's my basic points. Just a little piece of plastic follows the cam, and around that is the
Cam follower felt.
felt. Yep. What's the purpose of the felt?
Oil to keep corrosion on?
Well, it lubricates the cam and this. Okay. And what else would I say? Is there spring? There's a steel spring. It's spring steel that helps bring it back. And of course the actual points themselves, the actual points. And while I'm thinking about it, I believe at some point, hopefully if I had enough time to get to it, how do you clean points?
With a car.
Piece of paper.
No, you put a file in there and then you close them and just pull the file back and forth a couple times? Sandpaper. Put a piece of sandpaper in there and go back and forth. You guys never did that?
Nope.
All right, so what does Bendix say to use?
Business.
Cardstock. So you put it in and slide it back and forth.
No.
No?
Put it in, close it, take it out,
Yeah.
move the paper maybe, close it again.
That's it. Open it up, put the piece of paper. You know how many times I've done that in my life? Exactly this many times.
I just thought it was funny it said business card or something like
You know,
that.
I've actually, no, I take it back. I've done it a few times, but if I open up on an annual and I pull the cover off, and you can't do that on these anyway, so you're not looking at the points on slicks. But on Bendix, we would do it. We would just pull the back cover off. It's not terribly hard to get to. If it's on your checklist and you want to do it, you'd look back in there. And if it's oily or greasy, why are you trying to fix that? You got a problem. You got a bad seal. Change the seal. You know, don't go for the symptom, go for the problem. So if it's all oily and greasy, I'm just going to say, man, I got to take this apart, take your points, and then I can clean them. Put some new ones in. They're not expensive, that part, comparatively speaking. Okay, we have the condenser. Condenser, also called capacitor, also known as capacitor. Wired in parallel. To points. So when the points open, comma, there is a tendency for the primary current to arc across the points. There is a tendency for the primary current to arc across the points. Across the points. What happens? Well, this wears out the points. Wears out the points and prevents, well, I wrote it prevents the points from working properly. We don't need to write that. It wears out the points, and then we'll put 4 over here. Aids in rapid collapse. Of the field. Now, when you're running your magneto and you're watching it run, look down into the points. You're going to see a little bit of arcing back and forth. It's not a bright blue arc. It's kind of a orangish arc. It's not a lot, but you still get some down there, just the way it is. Put this one here. While you're getting everybody caught up. So I was whining earlier. Some of you didn't get to hear my whine, so I'll make sure everybody hears my whine. So my slick magnetos are, it's time for them to be 500-hour inspected. And so I went online and I looked at the 500-hour kit, which doesn't consist of a whole lot. And thought, maybe an overhaul would be better. But the overhaul kit was something like, it was stupid. It was like $900 or something. A brand new magneto was like $1,400. That's slick for you. I was going to get a electronic ignition on one side, so I called my buddy and said, hey, order up electronic ignition. I just texted him, and he replied back, have you really researched this? So I call him, what don't I know? He's like, man, I'm hearing a whole bunch of people are having problems with them. Don't get one. I said, all right. Capacitor also absorbs the induced voltage generated in the primary as the field collapses, as I'll put its own field collapses. All right, that brings me to
The secondary circuit.
secondary circuit. Well, I already drawn it, and I've already talked about it, so I can just write some notes. Okay, what parts make up the secondary circuit?
Secondary winding.
Secondary winding. Everybody should be playing this game.
Distributor block.
Block.
Not the distributor block. What comes next? What comes after the secondary winding?
Carbon brush.
What comes before the carbon brush?
High
tension.
High voltage.
High tension. Tab is the plate. Plate was the right idea. Tab was the perfect word. So secondary coil.
High tension tab.
What comes out of the high tension tab?
High tension voltage.
High tension voltage. He is correct. So you should be expecting to see high tension voltage come out of that. Some of you guys, when I'm watching you test your coils and stuff, I'm like, you don't really know where the stuff comes out, do you? So the high voltage comes out of the little metal tab, then it goes to the carbon brush, then to the distributor gear slash finger. I don't care which finger you use as long as you get it right. Finger to the distributor block. Yep, I'll accept that. To the
Spark plug wires.
spark plug wires, spark plug harness. To the spark plugs. To ground. Back around. All right, secondary circuit.
And then we do it again.
To the spark tube. Secondary circuit. Contained in the coil assembly. Contained in the coil assembly. What's inside the coil assembly?
Core.
The core.
Primary.
Primary.
Winding.
Windings.
Secondary.
Secondary windings. Okay. Let's see. Contained in the. Oh, I'm sorry. I should have.
Secondary.
It should have been one. Should have been secondary winding. Then this should have been a 1, and then this should be a 2. Two has over 100 times the amount of turns as in the primary. 100 times the amount of turns. As in the primary. I don't know exactly how many wires it is in there. One of my sources said several thousand. Several thousand turns of very fine wire. Do I actually care how many are in there? I'm not going to build one. That's somebody else's problem. All right, secondary winding goes to the, now I think I know why you guys say distributor, because I may have had I got it flipped here, but goes to the, let's do it this way. High tension tab to the carbon brush, to the rotor, which is gear driven by the rotating magnet. Gear driven by the rotating magnet. Which way does a magneto turn?
Direction from the drive end.
Whatever's stamped on the data plate.
Whatever's stamped on the data plate. So what if it says it's a I was trying to think of SLN. SLN.
Left hand.
Left hand.
Left hand. Left hand from what? Pilot's point of view, right?
Yes.
Yes,
The
absolutely.
direction of rotation is when viewed from the drive end.
From the drive end. It's exactly the way you should say it. The direction of rotation is when viewed from the... Everybody should be saying it. From the... Okay, because you're not saying that right. The direction of rotation is viewed from, I hear all kinds of things. Well, from this side? The flange side? It's when viewed from the... What is viewed from the drive end? Direction of rotation of what component?
Magneto.
Any.
The magneto. What about a governor?
Same thing.
Same thing. What about an alternator?
Yeah.
Same thing. What about a generator?
Yeah.
Okay, everything. If you learn nothing else today, and I think some of you are on track for that, please remember that, because it's going to stick with you for the next, however long you're here, 5, 6 years. I don't know. Because we're going to keep asking that, right? We're going to get to generators. I'm going to say the direction of rotation is viewed from the, and you'll say, I don't know. Should I know this? Possibly, yes. Is it on the test? I didn't think you were going to ask me that. That's my favorite one. I didn't. Gear driven by the rotating magnet. Where am I here? Contains the distributor gear. Contains the distributor gear. Electrode. Also called finger. Contains the carbon brush. You should not pull your carbon brush out. You guys shouldn't, but in the field and you're working on, you have to. And it's a shame I can't really show you how to do it, but there's a spring in there, and there's a right way and a wrong way. If you take it and you pull it out, you ruin the spring. But if you take it and you kind of twist it and tighten it, as you're screwing it in and pull gently, they pop right out. So the spring is just, you have to kind of go with the way the winding of the spring is, and it just pops out. So it's like, yeah, you're winding the spring up, it gets smaller and it pops right out. Where was I? Rotor, and then what comes next? The distributor block. Distributor block. Where the high tension leads attach and go to the cylinder. Where the high tension leads attach. Where high tension leads attach. What comes after that? High tension leads. Or the harness, or the spark plug leads.
Just make sure when you say high tension, that's like high voltage, right?
Yes. I'll put spark plug leads. And then the spark plug. There we go. I kind of feel like I've covered what I have on my notes.
You've been covering it all week.
Huh?
You've been covering it all week.
I know. So if I was going to do the next thing, operation, which I kind of feel like I did. So I've only got like 8 pages of this. As the magnet is turned, lines of flux travel through the pole. You want me to write all this? Several pages.
Say it first and then I'll let you know.
Okay. Let me see. What have I got? 3 pages? Yeah. 2. As the magnet is turned, lines of flux travel through the pole shoes into the coil core.
Yes.
Okay. True. Flux periodically reverses but is constantly changing.
Also true.
The changing magnitude of the flux.
Yeah.
Wait a minute. I have like page 8, so I was trying to figure out. I obviously changed my notes and then whatever. The flux. Oh, there it is. Flux. The changing magnitude. The flux changes in magnitude. There we go. The voltage induced in a coil of wire is proportional to the rate of flux linkages. A flux linkage is one line of flux. This is too much. Faster the change, the more current will flow. I mentioned that.
Yep.
Flux linkage can be increased by more turns, stronger magnet, faster movement.
Yes.
This is why you recharge your magnet. So if your magnet starts getting weaker and weaker, your magneto is going to get weaker and weaker. If you start losing turns in your coil, then
It's gonna get weaker.
call me because I want to see what's happening. All right. There must be a change in flux to induce voltage. We've talked about that. No change, no voltage. Big change equals big voltage.
A lot of damage.
Direction of current flow. Nope, we don't need to do that. Lenz's law. The current that is established creates its own field that is counter or opposite to the applied. Should I say it again? The Lenz's law. The current that is establishes opposes the current that caused it. Remember?
Yes.
You okay?
Could you say that again?
He's like, look at me. So, say it again. Yes, I will say it again. The current that is established creates its own field, magnetic field, that is opposite to the applied, well, this is field, but I should say voltage, really. I like that better. Current. The applied current, which is going back to Lenz's law. As that current comes rushing in, you're going to build up an electromagnetic field that says, wait for a minute. Don't go. Don't go. That's right. I don't want you in here. And then once it gets in there and it's established and then the current tries to leave, it says, don't go. I'm lonely.
You're pretty cool.
Stay. I got used to you. Let's see. When flux is building, counter EMF opposes the buildup. Right? We talked about that. When flux is decreasing, it opposes a drop. When a coil is added, the static flux curve, I got that, changes to look like what I drew. Breaker points are designed to open with the greatest change when the greatest change of flux is happening. When is the greatest change of flux?
When the first primary flux
The
cycle-
greatest change of flux is right there. Well, if we look at the resultant flux curve, it just happens to be where I want the E gap to be, but behind it, that dotted line. So it's a little bit after the static. Breaker points are designed to open when the greatest change of flux is happening. The position of the points opening is known as E gap. How many degrees is that?
Plus or minus. 10 plus or minus.
Pass neutral.
Number of degrees past neutral that the
Points open.
points open is the correct definition. How many degrees is it? There we go. Depends on
The magneto.
magneto. It's not 10. Depends on the magneto. What is it for the Bendix magneto you're working on?
10.
Okay, but it's not the same for all of them. So if it's 10 degrees plus or minus,
4.
what should you set it at? 10.
10 and hope you're within that.
10. Let me see. We'll just finish this part up here, then we'll go on break. E gap is defined as the. You're my guy.
Oh, number of degrees past neutral when the plane's open?
Yes, very good. E gap is a number set by the manufacturer and adjusted internally by a mechanic. I feel like I should write this. I really do. So, what is this? What is he talking about? What is this craziness that's going on right now?
I just got lost for a second.
We were just kind of covering a lot of things here that I've really covered, and I didn't want to spend the next hour writing all of this stuff, so I'm going to stop right there. But now that it's 8:20, I think it's a good time to stop, and I know where I'm going to pick up. So.
Okay. Operation.